We ready? Let's do this. Welcome to episode 19 of Things Hidden. Things Hidden is an exploration of the intersection of faith and 6 factors that surround faith: religion, physics, evolution, consciousness, philosophy, and technological innovation. The purpose of Things Hidden is to bring people into a closer relationship with God, and through that process, coming into a closer relationship with God myself. Okay, here we are. Episode 19. Today we'll be talking about artificial intelligence. But before we get started, do me a favor. Smash that like and subscribe button. And if you're really feeling generous, please leave a comment on the video. It helps Things Hidden reach more people. Okay, as I was saying, today we will be talking about artificial intelligence. Depending on your social media algo, you might have been feeling like you've been getting a lot of AI doomer content lately. If you spend any time on Twitter at all, you probably saw the Citrini AI doomer piece that came out a couple weeks ago. And there's been plenty of other chatter like this too. AI is going to take all the jobs and it's going to leave everybody destitute and homeless, and the global economy is going to collapse, and AI is going to turn evil and destroy humanity. You know, we've really been getting bombarded with this kind of thing lately. I feel like AI doomer anxiety reached all-time highs in February. There's just so many of these things going on. And this content, it really is incredibly easy to find if you go looking. And in large part, that's because AI doomer content gets clicks. It gets you eyeballs. It feeds on our own fears that were forged through millions of years of evolution. And then those fears are delivered seamlessly to your phone, endlessly for free. That's a little tough, right? But we're not going to be talking about AI doom today, at least not mostly. We're going to be talking about happy AI stuff today, mostly. In particular, we're going to focus on the application of AI in the biotech space. It seems to me that this is a somewhat undercovered area. The chatbots get all the airtime because everybody is actually using them for various things, both in their personal lives and professionally. And I get that. But the stuff happening with AI in the biotech space, it's amazing. And there's also this direct connection into longevity here as well, too. AI is being used to systematically cure the reasons that people die. The expectation is that increasingly more people will begin living increasingly longer, drastically longer. So that's what we're going to cover here today, and a bunch of different clips from world-class experts. And I will make sure to include all of those videos in the description below. Now, I've tried to pick clips here today that leave the discussion of AI and biotech at a relatively high level in terms of addressing this topic, because you can really get down into the nitty-gritty of all of this stuff like very quickly, and it just all goes completely over my head. So, do not mistake me for some sort of like AI biotech expert. I know next to nothing about this topic, and I understand even less. But you can listen to world-class experts, the smartest people in the world on this thing. You can listen to them talk about what they're doing and what they're seeing and what they're expecting, and then you can assess that for yourself. And that's what we're going to be doing here today. Okay, first up, we have an interview with John Jumper by Hannah Fry. John is the co-founder of AlphaFold, the enormously revolutionary AI system created by Google's DeepMind. AlphaFold effectively solved protein folding. John won a Nobel Prize for his work on AlphaFold, so he is definitely a guy worth listening to on these sorts of things. And we'll jump into this conversation to hear John talk about the problem and the solution that AlphaFold came up with.
I mean, we're still only 5 years on from that CASP breakthrough, really, when AlphaFold 2 smashed the prediction challenge. Did you realize at the time the potential significance of the work that you were doing?
We were sure of two things and totally unsure of some others. I think the two things we were pretty sure of, we were very sure it worked even before we entered CASP. Mm-hmm. It measured very well. We knew about how we would do in CASP. That we understood, and we were careful. We knew that we had solved this grand challenge, that the normal thought in a grand challenge in science is that you'll solve it, and there'll be a great celebration, and then you will go build effective, useful systems that use the ideas that enabled you to solve the grand challenge, and that this was kind of the beginning of an era. I think the real shock to me is, those weights that we train, that system, that piece of computer software has been so incredibly practically important to scientists working in this field to this day, that the actual bit of software is used that makes this difference in all these different application areas, all this different type of science published on top of this as a black box computer program. And the extent to which that has entered into scientific practice has been really, I think, beyond my imagination.
Yeah, I mean, it's really difficult to overstate the genuine significance that this has had. I saw one thing where AlphaFold was described as the most useful thing that AI has ever done. Right, that hasn't sort of landed with the public yet, has it?
I think it's hard for people to appreciate, and you work in science communication, how very hard science is, how very hard curing disease is. We have to work extremely hard to get small bits of knowledge about how, say, the cell works, how the body works, for protein structure prediction or protein structure, what AlphaFold does. I think it's hard for people to appreciate this process, takes a year in the lab. I've seen PhD theses that are progress toward determining the structure of X. And that doesn't mean they finished it, just they feel like they're a little bit closer and they need to graduate. I think
of one protein.
Of one individual piece, and the notion that we'll turn that work into a machine that gives you a really good answer in 5 minutes. And then that enables so much more work downstream of it. I think there's something like, I haven't looked at the recent number, but 35,000 different scientific papers that cite AlphaFold, 35,000 different contributions to our understanding of biology that build on top of this advance. And I think the right kind of way to think of AlphaFold is not certainly that we've solved all problems in biology. We very much haven't. I think for this slice of biology that cares about what structures in the cell look like, structural biology, maybe we've made it 10% faster overall across the whole thing. We've amplified this enormous effort and societal expense. And then ultimately we will have transformative science. And there's certain narrow areas, say protein design, that are just being transformed by this understanding.
I think one of the ways for me that really demonstrates just how important this was as a breakthrough was the way that biologists reacted when you published the 200 million protein structures. Just tell me a little bit about that, because you just put it out there, right?
Oh, yeah. So the original release was a bit smaller, but was still, I think it was like 400,000. What I remember was there was maybe a week in between when we had put out our code and the real experts were playing with it. And they were like, this really works on hard problems. But all the other biologists were, no, these can't be real hard problems like I work on. And then, of course, we put out this huge database, AlphaFold database. And people are like, well, let me just see how dumb the AI engine was and click on their protein of interest, I think, expecting to make fun of it. And then they sat there and they were amazed. I saw this comment from someone on Twitter saying, how did they get a copy of my structure? How did DeepMind get this thing that I had done and not yet published? Like they couldn't believe that this was like literally a machine doing years of painstaking work, like this all at once kind of a flash. And what was, I think, also amazing about it is how rapidly this turned into a community understanding of what AlphaFold does, what it doesn't do, for example, not sensitive to single amino acid changes, and how to build this into their workflow and do work on top of it. I thought it would take kind of years for people to really figure out what's the right way to build it in. How do I make sure that I look at, the confidence measures where AlphaFold is saying this looks like a reliable answer, this doesn't. And this happened within a matter of months, that science is a community, that all people developed this incredibly rapid, not totally perfect, but actually really good understanding very, very fast. And so people were doing excellent science on top of AlphaFold. We released this in, I think, July or something like that. And people were almost immediately doing really excellent science on top of it, that really cool work was coming out by the end of that year. And I think that's just a testament to how much scientists are looking for really effective tools that help them push knowledge forward. And then when they find it, they use it well.
Yeah, you heard Hannah mention AlphaFold as the most useful thing that AI has ever done. And John is a humble guy, so he didn't actually respond to that claim directly, but he certainly didn't shoot it down. And then John goes on to frame how difficult this type of work was. People doing their entire PhD thesis on making progress, not solving, making progress towards solving the folding of a single protein. So people work on this for years. And now AlphaFold is a machine that gives you the answer in 5 minutes. And John's team released the mapped out structures for 200 million proteins. Just a stunning innovation with enormous ramifications. Okay, next up, we will hear John talk about creating brand new protein structures.
Step to all of this, though, if you are predicting the shape of proteins and then using those models to interpret the function of proteins in the human body, does it then go on to designing new proteins?
Oh yeah, people they've looked at these beautiful proteins and they said, I wish humans could do that, right? And so there's been all this exceptional work. And in fact, a lot of it done at David Baker's lab, who with Demis and I won the Nobel. And AlphaFold has actually been shockingly transformative at this, at saying, well, how do we go from now we've built these computational systems that understand it, how are we going to design our own proteins? And in fact, a large portion of new approved drugs are proteins, normally antibodies discovered initially in very, interesting ways, injecting mice or llamas with something that you want to build a protein against and using their natural immune system to find it. But we are starting to talk very seriously about how are we going to design proteins to have the effect we want. And it turns out that the most important part of that is that you can design many things you think might work. It's extraordinarily, it takes a long time. It's difficult. It's expensive to test in the lab. So what's been so important there is using AlphaFold as a proxy for nature, is trying to say, how do we integrate AlphaFold's understanding of how proteins stick together when they do? How do we use that to maximally make a signal for protein design? And people have gotten extraordinarily successful. They've gotten really, really good at getting proteins to stick just where they want.
Wow. Okay, but hang on, because that wasn't the original intention of AlphaFold, to see how proteins stick together.
Wasn't the intention of them to see how they stick together. In fact, that was an early surprise from Twitter, where two different people said, if you want to know if two proteins stick together, we were busy making a multi-protein, properly done system. They said, well, just take those two proteins and put some random amino acids in the middle and see if they stick together that way. And that was the best system in the world for seeing if proteins stick together.
Wow.
We didn't think we were making a system that could help people design proteins in a really deep way. We thought we would go use this fundamental breakthrough and go on and do it. And then people said, actually, it already works. And I think it was this grand story that does show up again and again in AI, so maybe we should have expected it, that if you train a model to be really, really good at a task, it has to learn a lot of deep facts. If you want to be really good at structure prediction, it learns some deep facts about how proteins interact. And if you do just the right experiments, you can kind of access that knowledge. But there was this whole field of what I think people started to call AlphaFoldology, where people would find out which things work. They would just treat it as this really cool black box that they could start experimenting with and try their own ideas on. And I think there was a lot of really great science that has been and continues to be done in that vein. We're still figuring out, there's starting to be work on how do we make enzymes, proteins that do chemistry, how do we do really complicated, sophisticated stuff. We're still, nature would still laugh at us on our ability to design proteins, but we are starting to develop these really interesting tools that are maybe therapeutics, that are also maybe ways to interrogate the cell, that you can bring two proteins together and see how the cell changes because you do that. I think we'll get this interplay in not only the tools we use for therapeutics, but now our ability to poke the cell in exciting ways, to interrogate it. And every time we develop that, we'll develop a more interventional understanding of the cell that we will bring forward to medicine and synthetic biology.
Is this AlphaProteo that you're describing here?
So the AlphaProteo is Google DeepMind's internal effort to do protein design and thinking about problems in binding and enzymes and really trying to figure out how do we get, especially for these super hard problems, how do we get reliable systems? And I think what we're seeing is in the design space still is a lot of success, but when you're actually designing proteins, you have to go to the lab and test them. There's no other way to find out, and then finding out the right ways to predict if they're going to work. And the AlphaProteo work has shown that we can get further and further in doing this.
Give me an example then of some of the type of proteins that are the target, right? That like would be nice to be able to design.
You know what? I think if you ask any protein designer, they will have a favorite. And their favorite is really, can we make proteins do things like carbon capture? Can we actually, build enzymes that meaningfully contribute to, address climate change? I think other ones that you really see, for example, degrading microplastics or environmental plastics. I think one of the things also, though, I'll say as a caution is that for all of these, when you talk about doing a real application, just like people's conception of drug design is get molecule to stick, drug design done, right? And that's not the case, right? There's so many more properties you need. You need it to be tolerable in all these ways. You need it to be pill formulatable. You need all these other things. Similarly, in enzymes, you might think, oh, well, you just need to make this reaction happen. An enzyme, right, is a protein that catalyzes a chemical reaction. But no, actually, you need to be able to do this many times, right, enough that you're not constantly having to make new proteins for each reaction. You need it to be fast enough. You need it to not do certain other reactions. You have all these other properties. And I think there's a lot more to be done as we think about going from, oh, maybe this is kind of interesting to this really, really works. Although in fairness, actually, interestingly, on kind of synthetically evolved enzymes, people are already using them. There's a lot of washing powder that has designed proteins, which I find fascinating. I think one of the few applications of designed proteins and something people would recognize.
Yeah, absolutely. How much harder is it, though, to sort of engineer biology than it is to kind of design than it is to just predict?
I'm very empirical. You should ask me in 3 years and we'll know. It's easier and it's harder. One analogy I like to say is if you're trying to figure out what an object is, and you might say, is this a bicycle? And I would see 2 wheels, a chain, some handlebars, and I would say, yeah, that's a bicycle. But having 2 wheels, a handlebar, and a chain doesn't make something a working bicycle. So when you're designing something, you have to get all the details right enough that it actually works. And I think we're still figuring this out in proteins. And right now, protein structure prediction is, let's say solve star, right? It's a very, very useful system. It's not perfect. Design is not yet solved, but I think that it is advancing rapidly. And I don't think we'll be still talking about protein design as incredibly difficult in 15 years.
Using AlphaFold as a proxy for nature. I mean, it's just an incredibly impressive statement. And then it's also just cool to hear John talk about the groundbreaking innovation that's occurred with AlphaFold in areas where they didn't even think AlphaFold would be applicable, like putting 2 proteins together. And then the next step with this AlphaProteo that he's talking about, now you're talking about designing entirely new types of proteins and then testing them and then putting them into actual use in things as simple as washing powders like detergents, but also as revolutionary as carbon capture in the atmosphere and degrading environmental microplastics. Fascinating. Okay, last clip here with John, and we're going to hear him talk now about the differences between narrow AI like AlphaFold versus artificial general intelligence, AGI, and artificial superintelligence, ASI.
Zoom out a little bit on AI and biology more generally. because this whole conversation, it's reminded me of something that you said when we last interviewed you a few years ago. And I've got a little clip that I can play you of what you said.
I think it's really important to remember that these are really powerful techniques that we've developed that are still far short of real artificial intelligence that you can talk about thinking and making decisions and everything else.
I think that's so interesting, because that was 2022, right? I wonder how you reflect now on that. Do you think that machines are beginning to sort of understand biology in an intelligent way now? Have you changed your mind?
I think that whether or not they can think, they're extraordinarily useful for solving problems. How far they are from AI or AGI, I think that's almost beside the point. I think the really, really interesting point is where we can characterize these systems as reliable enough. Do we find useful things for them to do? I think we need to be much more kind of utilitarian about it. And certainly machines like AlphaFold, I wouldn't necessarily apply the word think. And I don't know if we're in the situation, right, that we used to say, okay, intelligence was playing chess. Mm. And we should work on chess because once we have machines that play chess, we've basically got intelligence. And of course, we got machines that played chess really well and a superhuman level in 1994 was the Kasparov match. And that wasn't the path that led us to machines that can read and write. And so I think we always reach for these problems and say, well, this is the problem. Or people rather optimistically name something humanity's last exam, problem so hard that if you solve it, there's no point in posing problems to machines anymore. And I'm very interested in how do we find those problems that turn out to be so easy in a certain sense that we can do incredibly on them and build very useful systems before we build AGI. Those are the kind of science problems. And of course, you want to use related techniques to the people trying to build AGI. They're powerful techniques. But we don't have to get tied up in the philosophy. We can just build useful systems. In fact, I think the whole kind of industry is thinking a lot about how do we build useful systems that matter for people doing software development, that matter for people doing writing, that expand the nature of the problems we solve. And then we'll see if we end up with AGI, but we will certainly end up with useful systems.
Yeah, just a great reminder that narrow AI is currently making great strides in numerous fields. And so maybe AGI and ASI as goals just don't matter as much as the public discourse makes it out to be. Yeah. Okay, moving on. This next clip is Mark Zuckerberg and his wife, Priscilla Chan. Mark and Priscilla launched the Chan Zuckerberg Initiative, the CZI, in 2015. CZI is a nonprofit, and they, over the last handful of years, have really been almost entirely focused on the intersection of AI and biomedical science, biomedical research, biotech, that sort of thing. Mark and Priscilla pledged to donate 99% of their Meta shares to this initiative over the course of their lifetimes. And I went and ran the math, and the current value of those shares is over $200 billion. $200 billion. So that gives you a sense of the scale of what it is that the CZI is working on, what they are going for. And this first clip helps set the stage for that as well, too. They're going to talk about what they're doing and how they're going about it. So Mark Zuckerberg and his wife, Priscilla Chan.
I wanted to be able to help others. And I think training as a pediatrician at UCSF, I met a lot of patients and frankly, little kids and families for which we just had no idea what the problem was. And they might have a specific gene that they could name if they were lucky. Or they could be grouped into a bunch of other diseases and there'd be a general sort of PDF they'd print out, this is what we know. And then it was my job as an intern or resident to try to translate a few lines of information to how we were supposed to take care of the patient. And for me, that's when I really realized the power of basic science and how we need to work on basic science to advance the forefront of what's possible. And without that, there's I think of it as the pipeline of hope.
Yeah.
And why did you think you could cure all disease? Because that's like a very aggressive goal.
Do you want to answer that one?
Yeah, well, I mean, we're not going to cure all diseases, to be clear. I mean, the strategy is to help scientists in the scientific community cure all diseases. So the strategy is really one of accelerating the pace of basic science. And the theory that we had was, if you look at the history of science, most major breakthroughs are basically preceded by the invention of a new tool to observe phenomena in a new way. Right. So think about things like the microscope, right? And being able to observe bacteria, or, other fields, the telescope, or, but it's, just to use an engineering example, it's without those kind of tools, it's kind of like you're coding without being able to step through the code and debug things, right? So it's,
that's like the old days.
So our whole approach on this is basically, let's help build tools that will accelerate the pace of the whole field. And I think that there's a niche that I think fits that, because if you look at how funding works in science, the vast majority of funding comes from the government and NIH grants. It's parceled out into these relatively small grants that allow individual investigators to investigate usually pretty near-term things. And the development of these kind of new types of tools, whether it's imaging or building now a lot of AI things like virtual cell models, are longer term, oftentimes more expensive to develop. So think about on the order of 100, maybe 100 million to $1 billion over a 10 to 15 year period. And then you try to unlock those tools and give them to the scientific community to accelerate the pace. So that's kind of the theory.
Right. And then it seems like there's also something that's you don't really get credit for the tools in a lot of ways. I mean, we've been noted, we have companies that use your tools and they're very happy about it. But, I didn't even know that was the case. And so
that's why it's philanthropy.
Yeah, well, it is, but most people do philanthropy to get credit too. I mean, that's that's kind of a part of it. So how did you, I guess, did you think about that, or were you just like, no, this is going to work, and if it works, that's all we need?
We're super focused on actually making every scientist better, and beyond science, startup founders, because the point is we can't do this alone. And when we first set out the goal to cure and prevent disease by the end of the century, people, honestly, most scientists couldn't look at us with a straight face. And
you're crazy.
Yes. And it was true, because if you just decided to spend the money funding the next best grant for every single lab in the country, there's no pathway to that being true. But if you forced people to really think about this and okay, what is the most credible pathway to doing this? And what are the barriers to that credible pathway? Then we sort of got somewhere, right? They were there's no shared tools, or we're not working on big projects and building the right data sets. And we're okay, well, then we can start doing something about that. And so that's where the idea of building shared tools, because no one right now in the science.
Well, that's so interesting. So basically you're we're going to cure all disease, and they're can't be done. Why can't it be done? Well, because we don't have the tools. Okay. That's a pretty cool sequence.
Yeah, I mean, there's also this funny thing where the biology folks, I think, looked at it as if it were crazy ambitious. And then the AI folks are well, that's kind of boring. That's just automatically going to happen. I know, it's okay, there's something in between there that needs to be bridged. Yeah. And if you can kind of use the kind of modern AI tools in order to build the types of tools that biologists need. So that's a big part of how we think about our work.
AI's got to be the most overestimated and underestimated technology ever, simultaneously.
I mean, probably the internet early on. But we kind of think about ourselves and the work that we're doing at the BioHub as frontier biology paired with frontier AI, right? So there are labs that do frontier AI that basically, are building the most advanced models. And then there are lots of biological research organizations that effectively do very leading edge research to build, to either discover new data sets or looking to certain challenges. But so far, there hasn't been anyone who's tried to do both of those at once. And when you look at I mean, even something like AlphaFold, which is amazing, right? It was built off of this data set that was a public data set that had been produced decades ago, right? And what I think you have the opportunity to do if you do both of those together is produce specific data sets for the purpose of training AI models to build virtual cells that can do specific things.
Yeah, right.
So I think that that's like a pretty interesting zone to be in.
Yeah.
And of all the things that we've worked on, actually when we started CZI, we kind of actually focused on a number of areas. And what we found is just that the science research has had by far the biggest returns. So we've just doubled down on it over and over and over until now we're at the point that, we're 10 years in and BioHub is really the like main focus of our philanthropy at this point. But yeah.
The goal is to cure and prevent all disease by the end of the century. That's the goal. The strategy to accomplish the goal is to accelerate technological innovation. And, the question that wasn't posed directly, but sort of lingers in the background is basically like, how far do you get if you throw let's say $200 billion at this problem of curing and preventing all disease? And I think the answer is with AI, that's actually going to get you tremendously far and perhaps all the way to your goal of preventing and curing all disease. Crazy. Okay. Next, we'll hear them talk about virtual cells, which it's a little early to say right now, but could potentially, end up being a tool of the same caliber as something, like an AlphaFold that we just listened to John talk about here. So here's Priscilla and Zuck on the virtual cell.
Just simply not as standardized or QC.
Yeah.
Yeah.
Let's get into virtual cells. What are the great challenges, the grand challenges you would focus on? Maybe talk about what is the promise or the hope and maybe some of the challenges or where we're at with it.
Yeah, I mean, we think that this is going to be one of the most important tools at this point. Is basically building up the kind of hierarchy from proteins to just different structures within the cell to whole a virtual immune system or different levels of hierarchy. And we think that this is going to end up being like a very important set of tools for people to effectively generate hypotheses for different science work. Even before you get to the point where you're really running full experiments in it, you can come up with some estimate of how that might run. It will be useful for some of the precision medicine type examples that Priscilla was talking about a few minutes ago. But we think that this is like probably one of the most important sets of tools that you need to build. And it's not a single thing, right? So there's different angles to come at this from. The cell atlas data is helpful for understanding things on a cellular level. One of the kind of most important things that we're doing right now, there's this great company, Evolutionary Scale, who actually had a bunch of researchers who'd formerly worked at Meta on protein folding models, is joining a BioHub, and Alex Reeves, the leader of it, is actually going to be the kind of head of the whole science program, which is actually kind of interesting when you think about it, where it's like you have AI and biology coming together, and really it's like an AI person who understands biology is running it rather than a biologist who has some understanding of AI. I think just kind of speaks a little bit to where we think the relative weight of these things is. But I mean, we basically view, like Priscilla was saying with the different biohubs, then New York doing cellular engineering will basically make it so that you can have cells that can record different things that are going on around the body and share that data, and then you can build that into models. The Chicago Biohub being able to record inflammation and basically study that in order to kind of help understand that's a different data set. We have the Imaging Institute, which is we just trained our first set of models around that, which are the first spatial models around understanding the way that kind of cells look in different states. And eventually, just like you have this analogy on the kind of the industry side or in language models where you have different capabilities and then over time you train them into models and it gets more and more general, that's kind of the idea here. So we'll build the biohubs around grand biological challenges. The biohubs will build tools that will generate novel data sets. We will build models based on those, and then eventually combine the models into an increasingly general view of a virtual cell that will be useful both for scientists and hopefully startups and companies that are working on finding drugs, which is not our part of the whole thing, but I think is obviously a really important part of what needs to happen.
Yeah, and you guys think about risk all the time in terms of when you make investments. Like, I think the promise of being able to do virtual biology using a virtual cell model is you can actually take on riskier ideas. Right now, like grant funding can be hard to come by, and the wet lab work is expensive and slow, and it's not just, money, it's also time. And so you have to choose something that you think is going to have some likelihood of success to keep your lab career going. And so it naturally lends people to take on like some risk, but not a lot of risk, because they need to make sure that they are hitting like a certain percentage of the time to make tenure or publish or whatever they need to do. But if you had a virtual cell model where you could simulate really high quality biology, you could actually then start testing and tinkering on the computational side and like ask riskier questions, things that would have been expensive and costly in terms of time and resources to do in the lab, and actually see if there is promise doing the experiments in silico before you make the time and money investment in the wet lab.
Yeah, so you heard Zuck say he thinks it's going to be one of the most important tools that helps you have a sense of what the scale of this is. And Priscilla at the end was also just talking about, I think very interestingly, the ability, it's basically like the whole funding environment of scientific research and not being able to get like that far out in terms of being able to raise funding for things that are just highly, highly uncertain. And yet there's like this very long history with just inventing things and scientific discoveries and things like this, where it's like so often discovery happens by accident. And this virtual cell will allow for just like so much more just various different things to be tried. And then a lot of times some of the best stuff just sort of comes up in a way that you never imagined. There's like story after story like that in science. And you're just going to end up using this virtual cell platform to drastically decrease the cost of just running all sorts of AI-enabled experiments in search of cures to disease and dying. Really cool. Okay, next we're going to move on to a presentation by Kimberly Powell. She is the VP of Healthcare and Life Sciences at NVIDIA. There is no other company on planet Earth that is more at the epicenter of this AI revolution than NVIDIA, one of the most valuable companies in the world. And you hear the name NVIDIA constantly in the media. Jensen Huang is this like incredible visionary leader figure. And what you don't hear very often with NVIDIA is you just don't hear much about biotech, but they're doing a ton in it. And that's what we're going to, about to hear some of that now. And we're only going to watch one clip from this video. The whole video is really good, but it's also quite dense and domain specific with a bunch of jargon. And so it gets, like I said, like a lot of this stuff, it gets pretty deep, pretty fast. So we're just going to hit this one clip where Kimberly is talking about AI and robotics, or so-called physical AI.
This revolution is just beginning, but it's rapidly accelerating. We went quickly past the perception phase into generative AI, where we could really take the world's knowledge and then generate new things, into agentic AI that allows us to do things like act, produce work, do tasks, intent-based computing. And we're at this next frontier where not only do we have digital agents, but we're going to have physical agents, where we're going to embody AI into physical things. But in order to do that, we need to have AI that understands the physical world. And so you're hearing Jensen talk a lot about physical AI. Let me try to break it down for you. Physical AI is really about 3 computers that you need to do physical AI with. We've been working on these 3 computers for several decades. The first computer is to develop AI itself. all those perception algorithms, all of these large language models and all of the agents. And what you have recently heard of is our World Foundation models, where you're taking, potentially sensor information and turning that into action information. And so once you develop data AI, you need to have a place where you can test and train this AI and validate its AI in a place that isn't the physical world. Because in the case of healthcare, in the case of surgical robotics, for example, it's too dangerous. In the case of self-driving cars, in fact, it's too dangerous. We don't want to have to only deploy this in the physical world to find all those corner cases to teach a car what to do. And so simulation and being able to do synthetic data generation is a very important part of the 3-computer process that has now just become incredibly powerful, with the ability to do accelerated computing, true physics-based simulation, and now generative AI. And then finally, we need a real-time runtime computer. You need a computer in the robot that embodies the AI and can do things and make decisions at very low latency. So essentially, you need a runtime computer. So 3 computers: a training computer, a sim computer, and a runtime computer. We've been working on the AI computer for a long time, and we make it domain specific. One of the platforms that we've worked on with a large ecosystem, many of you in the room, is MONAI. This has become the standard for medical AI development. Over 4 million downloads. We're talking several thousand papers now written using MONAI. So many contributors. We're still winning competitions with MONAI. And so we're so excited about the traction here. We've been working on it for 5 years, but it's now taking its next leap, and that is MONAI multimodal. And we've created the ability to, be able to work with all of the healthcare specific data. It's not easy. DICOM, text, surgical video, electronic health records, different omics data. So we create all of the data I/O transformation such that we can build these models in the first place. We then create models, multimodal vision language models that understand 3D imaging and text. It's different than when you're just doing 2D imaging and text. It can understand surgical video and text. We can incorporate now reasoning. And so we also complemented these models with an agent framework. The ability to put something like a radiology agent together that can essentially, what's not so easy to see here, is describe its chain of thought reasoning, providing the healthcare industry with a level of transparency that's, frankly required. We want to understand the chain of thought. We want to see the transparency, but we want to be able to use these very powerful tools. And so MONAI multimodal, we've contributed ourselves a couple of reference agents. So a radiology agent that has reasoning and can do report generation, or a surgical agent that can do information retrieval, or it can be a note taker while you're in surgery, an AI watching the video and can take notes. And we're also working with, of course, great contributors and collaborators from Mount Sinai and RadImageNet on essentially a 3D vision language model and a chat CT model from Zurich. And so we're going to continue to expand this, but this is starting to put the power of multimodal into the hands of every developer. So that's computer number 1, the AI training computer. It's now multimodal, it must be, and it can be agentic. Computer number 2, we've also been working on for some time, is NVIDIA Holoscan. This is our multimodal real-time AI sensing platform. So think of this as the brain that runs on the device. On the edge, can also run in the data center, but it's a real-time sensor computing platform. Today, we're announcing Holoscan 3.0. This is an amazing launch of this platform. It has, fantastic new capabilities to allow for essentially dynamic flow control. So you're going to want to, at runtime, depending on what's coming in from your data, that sensor data, you might want to make different decisions on how you're flowing through these image processing pipelines. And so now at runtime with dynamic flow control, you can do that with the new Holoscan 3.0 without all the crazy complicated coding. So we're just making this platform super capable for the age of agentic AI and physical AI and robotic AI by introducing some of these incredible features. And we have just so many amazing use cases for Holoscan.
Yeah, I mean, I don't know if that amazed you. It was amazing to me. You can see how much progress has already been made. This stuff is happening right now. As she was saying, NVIDIA has been working on this for decades. This Monai, this Holoscan, multimodal models that are incorporating text and surgical videos and a bunch of other inputs and combining it all together and synthesizing it into solutions. And then these solutions providing full chain of thought reasoning. So you can see exactly, why the AI decided to do this and then do that and so on and so forth. And, for as powerful as it is right now, like just imagine where it's going to be in 15 years when, the underlying compute power is 1,000x or 10,000x where it is right now. All of a sudden, this idea of solving dying doesn't seem that far-fetched. Okay, next we're going to move on to George Church. George is one of the GOATs for sure. He was one of the fathers of the Human Genome Project and one of the fathers of CRISPR. He's an absolute legend. He's also a great communicator. And in this first clip, you're going to hear him talk about the timeline for solving aging.
Let's start here. By what year would it be the case that if you make it to that year, technology will keep progressing to such an extent that your lifespan will increase by a year every year or more?
Right. Escape velocity is sometimes what it's called for aging. Different people have estimates, and all of those estimates are, including mine, are going to be taken with a big grain of salt. I think that mainly looking at the exponentials in biotechnology and the progress that's been made in understanding, not just understanding the causes of aging, but seeing real examples where you can reverse subsets of the aging phenotype. So you're getting close to all of aging. In other words, you're seeing, instead of just saying, I'm going to fix the damage in this collagen, in this tendon, in this limb, you're saying, I'm going to change a lot of things that are common to age-related diseases, and I'm going to get more than one at a time. I think looking at those two phenomena, the exponentials in biotechnologies and the breakthrough in general aging, not just analysis, but synthesis and therapies, and a lot of these therapies now making in the clinical trials, I wouldn't be surprised if 2050 would be a point, if we can make it to that point, 25 years. Most people listening to this have a good chance of making it 25 years. And the thing is, it's not going to be some sudden point where you're going to be, so sick 25 years from now that it's like hit or miss. It's more likely that you're going to be healthier 25 years from now than you thought you were going to be. There may be probably not some law of physics, but some economic or complexity issue that we don't know about that becomes a brick wall. I doubt it seriously, but we'll have to see.
Given the number of things you would have to solve to give us a lifespan of humpback whales.
Bowhead whales. Yeah.
Sorry, yeah.
200 years, yeah.
Is there any hope for doing that from somatic gene therapy alone, or would that have to be germline gene therapy?
Probably there's...
Just real quick to explain what Dwarkesh just asked there. Somatic gene therapy, this is changes to the DNA of non-reproductive cells in a person. So those changes will not be inherited by the offspring of that organism. And then germline therapy modifies reproductive cells or embryos and thus passing along the genetic changes to future generations. So just a quick explanation on the question there. and we'll jump right back into it.
From somatic gene therapy alone, or would that have to be germline gene therapy?
Probably there's a lot of forces pushing it towards somatic. For one, there are 8 billion people that have missed the germline opportunity.
Yeah.
Let's say doesn't apply to us, the two of us and everybody listening to this. And, you know, you have to be very cautious when you say something's impossible. It's safe to say it's impossible to do it this second, but you don't know what's going to happen tomorrow or in the next decade or something. So I think there's a lot that could be done, in particular, since aging is a fairly cellular phenomenon with proteins going through the blood and other factors going through the blood, the signaling and so forth. You could imagine if you replaced, let's say, every cell in the body, every nucleus in the body, it would suddenly be young again, right? Without going all the way back to the embryo and forward again. And there's various other things that are just short of that. If you replace the cells, they'll fit into that niche. They might displace the old cells. You know, that's certainly within the realm of modern synthetic biology is for cells to take over niches. I think the hardest part is the brain, but even there, you know, there's some evidence that if you even though the brain doesn't really use stem cells that much, you could artificially bring in stem cells and they could artificially fit into a circuit, learn the circuit, and then displace the old ones in some way.
Ship of Theseus kind of thing in the brain?
Yeah, exactly. Ship of Theseus. Having, trying to maintain the connections and the memories. But there's some fairly straightforward experiments that need to be done before we can really even estimate how hard that problem is. Or, very often there's low-hanging fruit that people just think is improbable, but it's there because biology has all these gifts that, where just hands over to us levers that we can flip, like vaccines is an amazing gift. It didn't have to exist, but they do.
Yeah. Is there an existing gene delivery mechanism which could deliver gene therapy to every single cell in the body?
There is nothing close to that today, but there's no law of physics that would prevent it. There's going to be practical considerations, how many injections do you need to do to achieve that goal? But we're getting better at targeting tissues. So for one of my companies, Dino Therapeutics, showed they could get 100-fold improvement in targeting neurons in the brain, which is a big deal. Now, and that was just one little campaign that they did. One experiment involved a lot of AI and a lot of testing of millions of different capsids. If you did that with cells, or the capsids are fairly limited in the diversity and the structure that it could change to, but cells that have even more possibilities, I think you could probably get delivery to everything. And the question is, how close to 100% do you need to get, right? And it's going to vary from tissue to tissue. For example, for some therapies, you just need to get 1%, because that 1% can produce some missing enzyme, and the 1% doesn't have to necessarily be in its normal place, right? You can turn a muscle into part of the immune system temporarily for a vaccine. You can, an enzyme that's normally made in, let's say, the brain, you could make in the liver, right? If the point is just to get it into the blood. So I think that's moving along quite well.
2050, the escape velocity for aging, gaining more than 1 year of life expectancy for every year that passes. And, this guy's like the Kobe Bryant of genetics. And he's telling you that when he looks at the exponentials in biotechnology combined with the just increases in knowledge about what aging actually is, he says 2050, 25 years from now. It's hard to wrap your head around how humanity's relationship with disease and death could change so drastically over such a short period of time. But that's what this guy's telling us. Okay, we're just going to do one more from George, although this whole conversation is excellent.
When you get the right idea, it's not hard to recruit people. I mean, for example, when Feng Zhang in my labs brought out CRISPR, we just got 10,000 requests in the next 2 months for people that wanted to duplicate the system. And so that's what I hope will happen with the non-standard amino acids and the using AI for protein design and making new materials. Hopefully that will recruit tens of thousands of people overnight. Yeah.
Are you more excited about AI, which thinks in protein space or like capsid space, or like just, it's like predicting some biological or DNA sequences? Or are you more optimistic about just LLMs trained on language, which can like write in English and tell you, here's the experiment you should run in English? Which of those two approaches, or is there some combination that when you think about AI in bio is more promising?
I'm much more excited about scientific AI than I am about language AI. I think languages were in pretty good shape already. And what worries me is that to get to the next level of language requires AGI or ASI, so artificial superintelligence. And that's very dangerous. I don't think we have quite figured out how to. And there's a lot of safety organizations and a lot of safety rules and so forth. And I think what typically happens when there's an intense competition is those safety rules get undermined and pushed aside. But even if they weren't, I don't think we understand our own ethics well enough to educate a completely foreign type of intelligence. I mean, we barely know how to pass it on to the next generation of humans. So I think we need time to sort that out. And there's no rush. This is a completely artificial emergency. This is not like COVID-19 where millions of people were dying if we delayed the science. This is something where if there ever is a crisis, it's because we created it. It's not because we're trying to solve it. Yeah. Right. And so I think we need to go very slowly on AGI and ASI and double down on slightly narrower scientific goals. And even that we need to be very cautious about. We need to have kind of an international consensus on what constitutes safe AI.
I suppose we did build safe superintelligence. How much would that speed up bio progress? Is it just like there's a million George Churches in data centers, just like thinking all the time? Is it a 10x speed up?
I think it would slow it down. I think it would eliminate it because the first thing it would conclude is biology is not relevant to me because I'm not made out of biology.
I mean, suppose you get them to care about it. There's just like copies. There's a million copies of you in a data center. How much faster is bio progress? But they can't like run experiments directly. They're just in data centers. They can just say stuff and think stuff.
I don't think we have anything close to the assurance that we need that would be safe. But let's put safety aside for a moment. I think it's hard to. It's not only hard to calculate the bads. It's hard to calculate the goods. So I think it could be a complete game changer. But on the other hand, it's like if we said, we could get instantaneous transport all over the earth, right? Well, we could say, yes, that could be a game changer, but do we really need it, right? Is that really important? Maybe it would be more interesting to just have Zoom calls that are better, or just learn how to get everything we want in our kitchen and we don't need to travel anymore, right? So, be careful what you ask for, right? Because you could tip our priorities towards something that we really don't care about, where we shouldn't care about or might wish we didn't care about, right?
But I'm curious what you've still got to run the experiments. You still need these other things. So does that bottleneck the impact of the millionth copy of you, or do you still get some speed up? How much faster can biology basically go if they're just like more smart people thinking, which is a sort of proxy for what AI might do?
These are great questions, and I'm not sure. I don't want to misrepresent that I know the answers, but it's like the question of if you have 9 women, can you do pregnancy in 1 month? No, not present.
But you're working on that, right?
No. I mean, but the same thing is there may be certain things that doesn't take a lot of people. We just don't know. We don't have that much experience with having, thousands of Einstein type levels of creativity and intelligence simultaneously in a generation. And in fact, it's probable that we're all capable of being a bit more efficient if we don't have, distractions of mental illness, of, taking care of other people. Now, taking care of other people may be a very good thing. It may be that if we have no one to take care of, there'll be something bad that happens to us socially. These things are very complicated, hard to predict. I think right now, I think the baby step, or actually the pretty big baby step, is to eliminate diseases, or at least make it possible for people to eliminate their own diseases as they see fit.
Mm-hmm. You worked on Brain Organize and Brain Connectome and so forth. That work, how has it shifted your view on fundamentally how complex intelligence is? In the sense of how are you more bullish on AI because I realize the organoids are not that complicated, or it's very little information is required to describe how to grow it, or are you no, this is actually much more gnarly than I realized?
I think I always felt it was very gnarly. And I also felt that there was something that we could engineer. Certainly, we have made a lot of progress in at the broken end of the spectrum where the brain is severely challenged relative to average. There's thousands of a huge fraction of genetic diseases that are that have one of their consequences being that the child is developmentally delayed to such an extent that it's lethal or a lifetime deficit. And we know how to we know the genes involved, and we know how to do genetic counseling, and in some cases gene therapy and other therapies to deal with it. At the other end, we have reduction of cognitive decline by cognitive enhancement, which is showing some promise. But again, that's kind of like this early stage severe impediment to cognition has a late stage component. But what about how much information does it take to encode a brain? I'm not sure that it's that much less genome is required than if you just wanted to make a brain, because the brain is totally entangled with the body. You have a 10 to the 11th neurons, 10 to the 14th synapses. If you wanted to reproduce a particular brain, let's say, it might be, it's speculative as to whether it would be easier to do that by making a copy of it in silico, in some kind of inorganic matrix, or making a copy of it. Both of those are going to be hard. I would say that if you wanted to make a copy of a complicated book, it would be easier to take photographs of each of the pages and to completely translate it into another language, trying to get all the nuances of the poetry and so forth. If your goal is just to replicate it, and I think the same thing might be true of a brain. But replicating a brain probably involves a lot more information than synthesizing it. So, just to define this 10 to the 14th synapse is going to take a lot more bytes than the genome, which is billions rather than 10 to the 14th. But there might be reasons that you want to replicate a particular brain configuration rather than just make another animal that is starts from scratch as an infant.
Yeah, so a lot to cover in that clip. First thing I'll point out is just that that's the second time now that we have heard basically the championing of narrow AI and the downplaying or the desire to slow down AGI or ASI. George was specifically talking about that here in the context of safety issues, ethics issues. We'll put those to the side for the moment, but we are going to come back to those. And then he starts talking about, building brains from scratch or replicating an existing brain from scratch. And he gets into the complexities of the brain. He's talking about 10 to the 11th neurons and 10 to the 14th synapses. And it's unclear whether it's more difficult to make that out of silicone or whether to make that out of organic material, which is basically the difference between a machine learning neural net and our brain, which is like the OG neural net, a net of neurons. And this idea emerges of effectively recreating a human brain. Okay, guys. Yeah, sorry. Just a bit of bad news here. TED Talk just changed their copyright rules on YouTube. And so we can't show any of this video or any of this audio. We have included a link to the full video in the description here. It's 12 minutes. It's super interesting about this revolutionary Evo thing. It's relevant to the rest of the episode, but we just can't show any of it here on YouTube. We can show it on Spotify. So if you want to go watch it on Spotify as well too, we didn't have to pull it down over there. So just FYI, sorry about that. Next, we have the last video, and it's only from 9 days ago. This video explains a product called CL1 from Cortical Labs, and it is, it's wild.
Since launching the CL1 last year, we've been working hard behind the scenes to make sure our Cortical Labs API is as friendly, effective, and enjoyable for the user as possible. Today, we're excited to show you how, together with one of our collaborators, an independent researcher named Sean, we coded the first working version of Doom using the Cortical Labs API and running on a CL1.
So we showed that biological neurons could play the game Pong. This was a massive milestone because it demonstrated adaptive, real-time, goal-directed learning. But it took us over 18 months with our original hardware and software to get this to work. And Pong was much simpler. There was a direct relationship. The ball went up, the paddle went up. It was a direct input-output relationship. Doom was much more complex. Doom is chaos. It's 3D, it has enemies, it needs to explore its environment, and it's hard. So we've built a neurocomputing system to allow anyone to program this game.
To bridge that gap, we needed to translate the digital world of Doom into the biological language of neurons, which is electricity.
We built the CL API so that any user can interact with cells living in the CL1 with simple Python commands. Using the API, Sean managed to map the video feed from the game into patterns of electrical stimulation. When a demon appears on the left of the screen, specific electrodes stimulate the sensory area of the neural culture on the left side. The neurons react to that stimulation. We then listen to their response, the spikes, and interpret that activity as motor commands. If the neurons fire in a specific pattern, the Doom guy shoots. If they fire in another pattern, he moves right, and so on. Once our API was ready, Sean implemented this method with very minor tweaking in less than a week using the Cortical Labs cloud platform.
So, can the cells learn to play Doom? Yes. They're receiving information, they're sending commands to move their character around, they're able to find enemies, shoot. Is it an esports champion? Absolutely not. Right now, the cells play a lot like a beginner who's never seen a computer. And in all fairness, they haven't. But they show evidence that they can seek out enemies, they can shoot, they can spin. And while they die a lot, they are learning. But just like a human or an animal learning a task, the cells need feedback. They need to know what the right actions are and what the wrong actions are and how they can be trained to improve. While there's still a lot of work left to do on this, the exciting thing is we've solved the interface problem. We have a way to interact with these cells in real time and train them and shape their behavior to do things even like do. So the interface is solved. Next, we need better learning, better encoding, better rewards, better feedback. And we can do this with the CL1.
And explain what we're seeing here.
So this is the interface that basically show like all the vital stuff about the CL1, as long as the flow rate for the pump and the little window for the activity of the chip that is currently inside the CL1.
Can you show us the chip?
The chip is, I can show you the chip.
Now it's time to figure out how do we further enhance the learning to allow these cells in the dish not just to play the game Doom, but to really begin to excel at it and then take on even more complicated tasks.
So from here, we're ready to challenge the community to take a look at this field, take this platform and see what they can do with it. Work on the problem of, different ways of encoding information through stimulation, how best to do that, how to interpret the response of neurons to information that you've encoded.
The neuron's ability to play Doom demonstrates the flexibility of biocomputation. We're inviting developers and researchers to see what they can build. The API is open, Cortical Cloud is open, and the neurons are ready. The only question left is, what will you teach them next?
Yeah, okay. Turn human skin cells into stem cells, turn stem cells into neurons, do this 200,000 times, attach the 200,000 neurons to a silicon chip, hook the silicon chip up to the game Pong, and the neurons learn how to play Pong. Okay, that's too simple. Let's see if we can get the neurons to play the classic computer game Doom, a massively more complex game than Pong. Okay, yes, the neurons can learn how to play Doom like a beginner. Will they learn how to play the game like an expert? So yeah, bioethics. What is the morality of all of this progress? I think about it often, honestly. To me, that entire moral spectrum, it feels like a slippery slope. Because taking medicine to keep you from dying, that's okay, right? In fact, it's not just okay, it's amazing. It's a miracle of modern science. Same with surgeries, right? An amazing blessing that we have today. So many lives saved every year because we have the ability to do all sorts of different surgeries. What if there was a safe and simple, in-office procedure that newly pregnant women could have that would genetically remove all risk of all major congenital birth defects, different heart disorders and Down syndrome and these sorts of things? All of it. What if you could remove all of it? Would it be wrong to undergo that procedure? Would it be wrong to not undergo that procedure? You see what I mean, right? It's like, how far out do you take it? Designer babies, they're all 6'3" and jacked and tan with 160 IQs and kind hearts. When does genetic modification become immoral? Is making a human baby in a test tube in a laboratory, is that immoral? And why? Why does it suddenly become immoral? Why is it moral and good for a baby to have life-saving surgery, but it's immoral and bad to genetically design babies in a test tube? Where exactly on that spectrum does it flip from moral to immoral, from good to bad, from right to wrong? I don't know. I don't have the exact answer. It feels like one of these slippery slope gray areas. But it is a slippery slope gray area that is set to become increasingly more relevant. Hope that by the end of this, by this point in this video, I would hope that you would be as assured of that as I am, watching all these smart people talk about what's coming down the pipe here. And if I had to guess, China and Russia, they're already doing significant genetic modification experiments on humans, designer babies and test tubes and laboratories and like all this sort of thing, because their culture does not have the same reticence towards these kinds of things as we do in the West. And so if China and Russia, if they're already doing it and we in the West can't stop them, does the West need to be doing these same sorts of things? Because it's dangerous if we fall behind China and Russia in this regard. Because I don't know, maybe they're going to make some cyborg superhuman soldier thing, whatever, right? But like, it's just one of these weird gray areas. I don't know. It's just, these are tough questions. And I'm not entirely sure that the verses and the stories in the Bible that tell us not to act like God, I'm not entirely sure that they are directly applicable to these bioethics issues that we're talking about here. I will say, I would feel a lot better about this overall direction of scientific research and progress if the people conducting the research, if these people were strongly connected to God in their own personal spiritual lives. If the researchers that were doing this research, if they were doing it with a strong triangulation with and deference to God, the creator of all things, that would make me feel a lot safer about this situation. Unfortunately, that is not what we have in this field. It's hard to get exact statistics, but I do think it is safe to say that the large majority of researchers in this field are agnostics or atheists. My guess is very little, there's just very little triangulation with or deference to God that's happening in this work. And that's concerning. But all of this, it's undeniably exciting and it's extraordinarily positive. It's just that it comes with risk. And it really is a risk that we've never seen before as a species. There's no playbook for this, I don't know, except for maybe in some science fiction novels. And in my view, most moral issues, they really are black and white. Sometimes we like to pretend like they're gray because we know what the right thing is to do and we don't want to do it. So we sort of pretend like it's like this gray area where you're not sure exactly what the right thing to do is. But most of the time, most moral issues, they're black and white. This one, it's not so black and white to me. And in the rare instances in my own life where I've run across moral gray areas, my tendency has just been to give those to God through prayer and contemplation and reading scriptures and talking to other brothers in the faith. You just give this gray area to God and ask God to help you to have discernment to understand what to do. That's what I try and do in my own life. Certainly not perfect. It's what I try and do in my own life. And I think that would be the ideal approach with bioethics. And if that were going on, honestly, the whole situation would feel a lot less scary to me. But that's not what's going on. And that increases the risk of something negative happening down the line. So it's just that so much of this research, it is so positive for humanity. I hope that you got a sense of that from watching this video here today. It's just that it comes with these uncertain but spooky risks that no one even the experts can really understand very well. I think that's true for AI applications broadly, and I think that's, true for AI in biotech. Amazing technological breakthroughs that will almost certainly lead to tremendous benefits for humanity, with some risks that come along with it. Okay, that's it. I hope you enjoyed this. If you did, hit like and subscribe. If you want to sign up for the blog, it's in the description. If you're looking for the online community, it's coming soon. If you know somebody that would like this kind of content, send this to them. I really appreciate your time, and I wish you the best.